Yeah guys, good evening. So please type in the chat box. Is the audio and video fine? So good evening all of you. So please type in the chat box. Is the audio and video fine? All clear? Great. So this is the last but one lecture. Of course, in this lecture we'll introduce compressible flows actually. So this lecture will actually give an introduction to compressible flows. But before going for this lecture, oh just a minute. Oh, okay, fine. Yeah. So before going straight away, we have left some bit of psychometric process in last class. Okay, so basically dehumidification, humidification, these kind of things are left, and also adiabatic mixing of two moist air streams. Okay, so if two moist air streams are mixed together, what happens actually? Okay, so how we can calculate the end results, that also we'll see, and then we'll introduce compressible flows. We will talk about stagnation and sonic properties, like what are the stagnation properties, what is stagnation point we have seen in fluid mechanics. So what are the properties of the fluid at that stagnation point, because it's really important for us when we are analyzing shocks. Okay, so we'll talk about stagnation properties and also sonic properties. We'll see what is sonic in a bit, and we'll also talk about acoustic velocity and also area versus velocity relations. Okay, so these are the things that we are going to cover in today's lecture. And also, if you have a recap of last lecture, we have given a bit of just a minute guys, sorry, yeah, fine. So we have given a bit of introduction to moist air. Okay, so we have seen in case of moist air we have dry air and also water vapor, dry air and also water vapor. So in this water vapor we have seen the reduced pressure is actually tending to 0, so we treat it as ideal gas. So this is treated as ideal gas, correct? We have treated it as ideal gas actually here. And so ATD part for X is completed. With this part it is completed. Okay, with air conditioning part it will be completed. Okay, update, fine. So yeah, so after this we started looking at basic properties. We have started looking at basic properties. Okay, so what are these basic properties? We have seen in a given amount of moist air, what is the amount of water vapor which is present, that's measured with the help of specific humidity or absolute humidity. So we have calculated it as omega. Okay, and we have also seen at a given condition what is the saturation level of the air. For identifying that, we have calculated phi, which is the relative humidity. And also we have seen other properties like dry bulb temperature, wet bulb temperatures, then dew point temperature, dpt, and also there is one more quantity which is wet bulb depression. Okay, so we have seen all these things, and also we have seen to calculate this omega and phi. For calculating omega and phi, we have adiabatic saturation temperature, T adiabatic saturation temperature. Okay, so we are talking about adiabatic saturation temperature, and in yesterday's class I have shown you, if you know this quantity adiabatic saturation temperature, how can you calculate phi and omega. Okay, and then we have seen psychometric chart. Guys, it's a fast track course, so I haven't talked much about your psychometric chart actually. Whatever is useful for us, normally the specific volume and this enthalpy, we have talked only about those things. Okay, this dew point temperature lines, constant dew point, building up all these things you can find in some detailed course, or maybe in any I think I have not taken any YouTube detailed course, but yeah, you can find it somewhere. Okay, so just I'm giving you some brief of psychometric chart. Okay, so we have calculated this adiabatic saturation temperature. We have seen the apparatus for determining this T adiabatic saturation, and if you apply mass balance and energy balance, you can easily identify what is T adiabatic saturation. If this is calculated, you can calculate omega and phi of a given moist air sample. Okay, and then we have seen about psychometric chart. So basically we have seen the expression for the calculation of enthalpy. Okay, so we have also seen specific enthalpy. So to calculate this specific enthalpy, we got a relation 1.005 T degrees Celsius plus omega times of 2501, okay, let's say 01 plus 1.82 times T in degrees Celsius. So this is the enthalpy we have seen. This part corresponds to the dry air part, and this part omega times of this corresponds to the water vapor part actually. Okay, so this summation gives you the specific enthalpy of this moist air. And in case of psychometric chart, we have seen basically if you spot T, dry bulb temperature and omega, you can spot out different quantities like relative humidity, enthalpy, specific volumes, all this stuff you can point out. Okay, so psychometric chart, and then we have seen psychometric processes. We have started psychometric processes, and we have seen couple of processes which are something like which are something like sensible heating, and we have also seen sensible cooling actually. Okay, so we have seen sensible cooling, right? So we have seen these couple of things, and we have also seen how this looks in a psychometric chart. Basically these two will be horizontal lines. One, sensible heating, will be in the direction of increasing temperature at constant specific humidity, and sensible cooling will be a line in the reverse direction, means in the line a line in a horizontal line in the direction of decreasing temperature with constant omega. So these are the things that we have covered till the last class. Are you all clear with these points? You have any doubts at these points, or are you all clear? If you all are clear, then we will move forward. We'll see humidification, dehumidification combinations, then adiabatic mixing, and then after we'll jump to compressible flows quickly. Okay, are you all clear till this point? Everyone, come on, type it in the chat box. Done? Yeah, okay, so let us move forward. So basically this is how we are going to cover. Whatever is left we'll cover now. So continued. Now let us see a process C, or basically third process, heating with humidification. So what is this heating with humidification? Let's see. Heating with humidification. So let's say I have this can be done in two ways actually. I'll just show you the apparatus. So let's say you have a heating coil. Firstly, this is the heating coil, and let's say you have a sprinklers. Okay, so for example you have some sprinkler meanwhile where it sprinkles some atomized water form. Okay, so normally in case of chillings and all you have this. So let's say this is spilling some water, vapor. Okay, atomized water droplets, it's spilling atomized water droplets, so that evaporation takes place and it actually goes out. Okay, and this is your heating coil. This guy is your heating coil. Okay, so this is your heating coil, and let's say if this this temperature of vapor which is coming out is at the same temperature T2, this is T1, and finally the conditions here is T3. Let T3 is equal to T2, means you are sprinkling water actually at T2 conditions. Okay, normally what you can do, instead of putting this heater, if you sprinkle hot atomized water droplets, let's say if this water which is coming out is very hot, then this air which is present here will get heated. At the same time humidification also happens simultaneously. Okay, but just for the easiness in the calculations I am splitting it into two parts, a sensible heating followed by a humidification, adding water vapor to the atmospheric air. Okay, now if you take this control volume, and of course here air is flowing, you all know that air actually flows all over this region in this direction. Okay, so this is the direction of airflow. Now if you take this control volume analysis, let's set it up. So basically my intention is only to cover air. Okay, so this is the control volume analysis actually. Now here the properties are phi 1 and omega 1. So here the properties are phi 2 and omega 2, and here the properties are phi 3 and omega 3 clearly here. Okay, phi 3 and also omega 3. Now let's understand something here. If this part is only sensible heating, omega 1 is same as omega 2. Yes or no? Because right from this point to this point I'm not adding any water vapor. Okay, and T2 and T3 are same because we are adjusting the sprinkler to spray water exactly at this T2 temperature. So that's what we have. Now if you see this graph on a psychometric chart, and even before that if you do certain analysis, so this is the control volume. Now let's see for dry air, mass balance. First of all, applying mass balance. So if you apply mass balance, now dry air. So for dry air, tell me, if this is your section 1, for example, if this is your section 1, somewhere here is your section 2, and somewhere here is your section 3 actually. Okay, so you have section 1, 2 and 3. Then in case of dry air, whatever is the mass flow rate of dry air that's flowing at 1, this will be same all over. It doesn't change. Correct? Because there is no extra version for entry of this dry air. Now coming to omega 1 and omega 2, look, for water vapor, if you apply this for water vapor, then see what happens. Omega 1 is same as omega 2, And you can understand mass of water vapor entering section 1 is same as mass of water vapor entering section 2. But at section 3, sir, I have proved a lot after watch. Sorry, didn't get this comment. I think I'm skipping something. Acha, okay, thank you. Yeah, get. So let's continue. What I'm talking? I'm talking something now. This. So water vapor is same at this location and at the second state. Now at the third state, see what happens. M dot V3 is equal to M dot V2 plus whatever is this rate of water sprinkling. Let's say for example, if this is M dot F. M dot F is rate of water added to air. Rate of water added to air actually here. Okay, so this is rate of water added to air. Now this vapor available at this section 3 is nothing but vapor available at this section plus this excess amount of water which is coming inside, correct? So we have plus M dot F actually here. So what is the amount of water added? M dot F is equal to M dot V3 minus M dot V2 actually here. So this gives you M dot V3 can be written as omega 3 times M dot A, because all these three are same, minus omega 2 into M dot A, and omega 2 can be replaced with omega 1 because this part is sensible heating actually. So this gives you your M dot F is equal to omega 3 means exit minus inlet differences in specific humidities times M dot A. So this is how you apply simple mass balance, and you can calculate what could be the quantities. Now I want to ask you one thing. Omega 1 is same as omega 2. Can someone relate between phi 2 and phi 3? Phi 2 and phi 3. What could be the sign in between these two? Will it be positive or negative? Phi 2 and phi 3. Come on. I've told you T3 is same as T2. So please tell me. T3 is same as T2. If T3 is same as T2, then what could be the relation between these two? Just give it a thought. Think it once and then try to answer. You're welcome, tenacious beam. Yeah. Same. Pakka? Are you sure? Yes or no? Okay. Phi 3 will be definitely large. Why? Let us see here. Normally phi is PV by PV sat. Okay. So this is what you know. Now, whenever you are telling T2 is same as T3, this quantity will not change. Correct? Yes or no? They will be different. Correct? So PV sat did not change because the temperatures at these two locations is same. Correct? Now, when you are adding water at this point, definitely this PV increases. So phi increases. This is constant. This is your constant actually here. So that's constant because T2 is same as T3 actually. Understood? So if you want to calculate phi 2 and phi 3, definitely we'll calculate PV because omega is known to you. Omega 3 will be given. Normally the exit state conditions, if they give you omega 3 is given, then you can calculate what is this PV. Let's say if the complete apparatus is at 1 atmosphere pressure, then you can calculate PV. You can calculate phis at different locations. Okay. Because this temperature depends on pressure, no? This pressure depends on temperature, no? So if temperature is same at these 2 points, then this PV sat remains same, and addition of water vapor is proportional to, PV is actually proportional to mass of vapor present. So definitely as mass of vapor is increasing, then definitely PV will increase and phi will increase. Okay. Omega 3 is not equal to omega 2, na? Omega 3 is not equal to omega 2. See, because here the amount of water vapor present will be different from here, because in between you are sprinkling water. Okay, Nitin, got it? Why omega 3 is not equal to omega 2? Because at this point there is some amount of water vapor, and here some excess water is sprinkled inside. So definitely water vapor content increases at third section. Clear? Got it? Okay. Depends on pressure. Yeah, it depends on pressure basically, like this. PV. Okay. Now, yeah, got it? Now if I want to plot this on a psychometric chart, let's see how it happens. Psychometric chart. Psychometric chart actually. Okay. So if you see, dye bulb temperature, omega, kg of vapor per kg of dye air, and this guy is in degrees Celsius. Okay. Now initially, see carefully one thing here. For the first part, what you're doing, you're heating the substance. Okay, so T1 to T2, definitely we all know, since you're heating, heat is supplied in this, so T2 is greater than T1 clearly. Okay, so T2 is greater than T1, but omega is constant. So if you start this process, it happens like this. Okay, so this is 1 and this is 2 actually here in this case. Okay, so at constant omega, temperature increases. Now if you take T2 is equal to T3, then definitely what happens, your phi and omega increases. So if T2 is equal to T3, at constant temperature omega is increasing, definitely omega 2 is less than omega 3. So therefore 2 to 3 humidification part can be shown like this. And it's need not always mandatory that this is always a vertical line. If you sprinkle hot water, this line can actually shift. Means, see here, I'll explain you. This is state 3. Instead of showing this separately, you can always show any heating with humidification process as this line which is connecting this. Okay, because if you compare the inlet and outlet conditions, by the time if you see here and here, heating with humidification, because of this heating, temperature increases from T1 to T3, and because of humidification, omega 1 increases from omega 1 to omega 3, which you will see as a line where if you see this line 1 to 3 directly, temperature is increasing along this line because it is the increased direction of temperature, and it's also increasing omega. So 1 to 3 means starting from this point, if you go in this direction, it denotes heating along with humidification. Is this clear to all of you? Do you all understand? Heating with humidification. Okay. So every one of you, please type in the chat box. Is this clear to all of you completely? If T2 is not equal to T3, this line will be inclined. That's it. Anyhow, lines you can represent depending on your temperatures and omegas. But is this clear to all of you? Okay. Now let me, yeah, it's clear, right? Let me ask you a few things here. If I delete this anyhow, okay. So let's say I'm deleting this. This is the final result. Okay. So because of some process, your air went from this point to this point. Okay. So let's see. I'll make this line a bit short so that you can understand certain things here. So see here, if you have this as the line of heating with humidification, point 1 to point 2, and this is the heating with humidification, heating with humidification, heating with the humidification. Okay, so this is heating with humidification. Sorry, understood. Okay, good. Okay, so if this is heating with humidification, then let's see. If you take the lines of constant phi like this, then clearly you can understand. If you draw lines which are parallel to this, then if this is your phi 1 initially, and if this is your phi 2, then clearly you know phi 2 will be greater than your phi 1 actually. Correct? Yes or no? So please type in the chat box. Can you understand this? Means as you go in the right direction, sorry, this is heating with the humidification, correct? 1 to 2. So if you plot two lines which are passing through this, then I think I have drawn something else. Phi increases now as you go in this direction. Okay, here we have taken temperature increases directly. So that's why. Okay, this is a separate case. But normally if you see here, in this case, your phi 2 is less than phi 1 actually. Okay, the reason is when temperature is increasing very much. Of course, this we have compared only between this states 2 and 3. Okay, at same temperature if you are adding water, but this is at same temperature. Okay, so anyway, I'm using this because this is at this condition. But let's say in general, if you have like this, then as temperature is increasing, the PV saturation of the fluid will actually increase, and you will experience this. Your phi 2 will lie at a line on less relative humidity as compared to this point 1 actually. Okay, so phi 2 will be less than phi 1 if the temperatures are not same. Okay, if temperatures is same, then you can clearly understand the sign can change. If temperature is same, then it will be a vertical line. This point comes forward. Okay, like I have explained you in that case. Clear? So this is sensible heating with humidification, and this is the mathematical analysis for this circuit actually. Similarly, you can work out with cooling with dehumidification. So I'll just show you cooling with dehumidification. Cooling with dehumidification. Dehumidification means taking out water. Okay, so cooling with dehumidification. this is taking out vapor from air, taking out vapor from air actually. Okay, so this is taking out vapor from air. Now let's say in last class we have seen sensible cooling, and in this case let us see cooling with dehumidification. So see here. So let's say there is a cooling coil. Okay. So this is your cooling coil. Cooling coil. Now, if this is your cooling coil, let's say if the temperature of this cooling coil is Ts, then if Ts is greater than the dew point temperature, then this implies no dehumidification. Correct? No dehumidification. No dehumidification. Like we have seen the case of sensible cooling. So this is called the case of sensible cooling. Sensible cooling. Now, if Ts is less than TdPt, then what happens at this total pressure or at this PV conditions? If Ts is less than TdPt, by the time air touches this cooling coil, the air gets cooled so much that some part of the vapor present in the atmosphere will actually get condensed. Yes or no? Yes or no? Try to understand one thing. If this is the case, then definitely dehumidification occurs. Dehumidification happens. So dehumidification happens at this point. Correct? Yes or no? Yes? Thank you for the symbols. Yeah, so many love symbols are going. Thank you. But come on, just tell me this. Yes? If Ts is much less than this TdPt, then definitely water present in the vapor gets condensed and you can collect some amount of water. So how you can collect? That's the final state. Okay. So let's say if I connect some water here. So let's say I'm collecting some water in this. So let's say this is m dot f, and m dot f is amount of water getting condensed per unit time, or rate of water getting condensed, better. Okay. So rate of water getting condensed. Okay, condensed. And definitely let's say if this is state 1 and if this is your state 2 actually. Okay, so state 1 and state 2, then if you apply again mass balance for this mass balance, this talks about if you apply it for dry air first. If you apply this for dry air, m dot a1 is equal to m dot a2, which is m dot a, because only purely water gets out here. We are assuming nothing, no air actually goes out. Okay, so dehumidification can be done chemically as well. Yes, actually the reason for chemical dehumidification is endothermic chemical reactions. Okay, normally you might have studied in chemical reactions there are two types, exothermic and endothermic. You have studied in your schooling, 11th class or 12th class maybe. Studied exothermic chemical reactions and endothermic chemical reactions. Have you studied these two? Yes or no? Studied? Yeah. Normally, what do you know? Any example for exothermic chemical reactions? Yeah, I know all of you might have studied. Any example for exothermic chemical reaction? Any examples for exothermic chemical reactions? Which emits heat is called exo. Which consumes heat, or which consumes heat. Basically, for consuming heat, it will take heat from the surroundings, so surroundings gets cooled down definitely. Okay, which is endo. Any example for exothermic? Chuna means चुनाव means चुना को पानी में घोलना. Chuna means this wall paint. That's what white colored, cement kind of thing which you put in water. That's what, right? You're telling chuna. Fine. Normally, if you take a sodium piece, okay, combustion is a chemical reaction. Yeah, undoubtedly. So if you see, normally if you take some small amount of sodium and if you put it in water, you know what happens? if you take some small amount of sodium, say this much sodium you take, and if you put very small amount, okay, don't put very big amounts, it will cause disasters, but just put some small amount of water, sodium in water. If you throw it, then what happens? Do you know what happens? If you take some small piece of sodium and if you throw it in water, then you know what happens? It catches fire. Yes, it's not like always water stops fire. Water can catch fire. Okay, normally when I was in HPCL, when I was in Hindustan Petroleum, whenever there's if it's a rainy season, normally we won't be opening the devices very easily. Okay, it takes certain difficulty first to open the devices and do the maintenance, because some chemicals like this sodium, okay, as soon as they catch water, imagine who catches fire when touching water, but this little fellow does. Okay, so this sodium, as soon as it touches water, immediately it generates fire. Okay, if you can find some this YouTube experiments and all, in YouTube there are a lot of stuff. Guys, you know the beauty of nature, sodium is highly reactive. Okay, highly reactive metal, very highly reactive metal. Normally if you eat sodium, you will die easily, because inside your body there's a lot of water present. So if you eat sodium, it reacts with it, and you will die, or spot. If you inhale chlorine is again one very poisonous gas. Normally if you take in chlorine, if you smell chlorine and if you breathe in, if you inhale chlorine, then definitely it causes very drastic effects, because chlorine, these guys are highly poisonous. You might have studied fluid infectants, all these things. But these two, if you mix, you will get common salt, NaCl, sodium chloride, which you put it in curries and all, and you eat nicely. You make chicken curry, mutton, whatever you make and you eat, you will enjoy like anything. Okay, see, that's the beauty of water actually. Okay, nature actually. Sodium in itself is very dangerous, chlorine itself is very dangerous, but if you mix these two and if you form NaCl, it's salt, tasting normal, eating salt. Okay, so that's what you have. Clear? Fine. Yeah, anyway, here this low temperatures dehumidification, chemical dehumidifications can be done with chemical coolings actually. Okay, fine. Chlorine affects ozone layer also. Yes, CF2Cl2, we are studying now when nomenclature of efficients, chlorofluorocarbons, all this stuff. Okay, so what we are talking? Yeah, now if you apply this mass balance for water vapor, now this is a bit simple. M dot V1 is equal to M dot V2 plus this M dot F, which is coming out in the condensed form. Okay, and this M dot F, mass of vapor, this is coming out, is actually equal to omega times omega 1 minus omega 2, because omega 2 clearly decreases. Omega 1 minus omega 2 times of M dot A is what you have here. Okay, so that's what you have. If you want to apply energy balance, you can also apply that. Okay, so how do you apply energy balance? Look, energy balance, if you want to apply, like any control volume, same story, energy analysis, all this is done in your first basic thermodynamics. Okay, control volume, this, what do you say, steady flow energy equation. If you insulate this, definitely you will have to insulate this, otherwise heat flows out and cooling effect decreases. Okay, so you don't want that, so you will do heating at insulated conditions. So if you insulate this, and if this guy is the control volume, then let's see if this is M dot A at the state 1 and this is M dot A at state 2, and this guy is coming out at some temperature. Okay, so this is coming out at some temperature. Then let's see, H in is equal to H out for steady flow energy equation, because there is no heat, nothing, kinetic energy, no stuff. Now M dot A into H1 is equal to M dot A times of H2 plus this fluid is coming out at some temperature. Let's say for example this is the condensation temperature or saturation temperature at this PV. So at that particular location you can also decide what is this HF. Okay, HF is nothing but the specific enthalpy of this liquid water which is at this temperature Ts, or maybe if the dew point temperature is there, then at dew point temperature you can calculate HF. They'll give you the data, you can plug in this equation, then you can calculate maybe HF or whatever in this 6 terms. They'll generally give you 5 terms and you can calculate one. Of course in GATE exam questions of this tough standard are not coming, but just I'm teaching you because this is simple control volume analysis. Okay, so if you put sodium piece and chlorine gas in curry, will it behave normal? No, it don't behave normal. Okay, yeah, it don't behave normal. Please don't try it and eat it. Okay, you will be at problems. Fine. And if you want to plot this on psychometric chart, see how I can do that. this is temperature, T dry bulb temperature in degrees Celsius, and this is omega. Now tell me, if you are doing cooling, okay, if you are doing cooling, hi Ankit, good evening. So see here, if you are doing cooling, actually in this case, temperature should decrease because clearly you are doing cooling, and also because of this water which is getting condensed, omega will also decrease. Okay, so if you see, the line appears something like this. Okay, so this is how the line appears, 1 to 2 actually here. Okay, so this is how this 1 to 2 is basically cooling with dehumidification. Cooling with dehumidification. Dehumidification. Okay, cooling with dehumidification. So 1 to 2 is what you have. This is omega, and this is the variable temperature. So clearly temperature decreases, and if you spot lines of omega, definitely phi increases in this case. So phi 2 is greater than phi 1. So if you want to generalize all these processes in a psychometric chart, I'll just tell you. See here. I'll just show some generalization for you. You guys want to name those processes. Okay, now that you are happy, so see, let's say if this is the point, for example, if I go in this direction, let's say this is my point 1 in all the cases. If this is my point 2 and this is dry bulb temperature, then this is omega, this is degrees Celsius, then 1 to 2 is nothing but your simple humidification. Yes or no? At constant temperature you are doing humidification. Okay, so this is just humidification because omega increases with constant temperature, so this is pure humidification. Similarly, if I do 1 to 3 something like this, 1 to 3 something like this, then clearly you know in this case temperature is increasing, so definitely some heating is happening, and omega is constant, so there is no humidification that's taking place. So heating, sensible heating actually. I have told you what is bypass factor and all in yesterday's class, correct? Did I tell you what is a bypass factor in case of cooling? In case of cooling, did I tell you like what is bypass factor? I've talked. Did I give you the definition of bypass factor yesterday? Loss in the cooling effect by maximum possible cooling. Did we talk about that? Yeah, we have talked, right? Okay, good then. So this is sensible heating, and if you see in the previous day analysis, when we are talking about sensible heating, the graph started something like this, horizontal line with constant. Okay, and let's say if you go this way, this is 4. Okay, so 1 to 4 is nothing but your dehumidification. And normally if you see this 1 to 5, maybe something like this, if you keep at constant omega, so 1 to 5, if this is your process, then 1 to 5 is nothing but your sensible cooling. Okay, and anything somewhere in between these two will be combination of these two. It's like, for example, if this is east and north, then this is northeast. Okay, so similarly, if I plot something like this, some curve like this, and if I call this 6, then can anyone tell me this 1 to 6 is called? It is in between sensible heating and humidification. So this 1 to 6 is nothing but heating with humidification. That's it. Okay, so combination 1 to 6 is heating with humidification. Okay, so heating with humidification. Similarly, if I take for example this guy 1 to 7, say something like this. Okay, so this is 1 to 7 maybe. So this guy is 7. So 1 to 7 is 1 to 7 cooling with dehumidification. Basically, you see this looks like that. Okay, so cooling with dehumidification. Okay, so cooling with dehumidification. Similarly, you can plot any between these two. This is actually cooling with humidification, means let's say if you are putting some very cold water into the atmospheric air, then temperature decreases, at the same time humidity also increases. Similarly, this is heating with dehumidification. Okay, so let's say for example, if you, this process is generally not very much feasible practically to do, so we generally don't go here, but this 6 processes which I have done here will be much in day-to-day life we keep using them at many points actually. Okay, now let's go to one last thing before we go for some problems, some numericals. Adiabatic mixing of moist streams. adiabatic mixing of two moist streams. Okay, so adiabatic mixing of two moist streams actually. So let's see how we can do that. Let's have certain configuration basically. Fine. Okay, so let's say this is an insulated because it's adiabatic mixing. We don't want energy to go out unnecessarily. So let's say this is adiabatic case. Okay, now this guy is state 1 1, this is 2 2, and this is state 3 3, or sections 1 1, 2 2 and 3 3 actually. Okay, now let's say through this we are getting some amount of air which is m dot a1, and this is at a conditions of t1 phi 1 omega 1, and we are getting some other mass of air through this. This is at a conditions of t2 phi 2 omega 2, and this guy over here is something like m dot a3 t3 omega 3 and phi 3 for example. Okay, now let's say, sir, in the Ladakh or cold places what will be the condition? Condition in the sense like temperature will be generally very low. Okay, something it's like very cool Bangalore. Okay, now anyway, so yeah, if you have this 1 2 and 3, so basically if these two streams mix, what could be the outcome properties? That's the main story here. Now again, if you see, you take the control volume, you take this control volume for example to do the analysis. So let's say this is the control volume. Okay, so this is your control volume for example. Now if that's your control volume and this device has to operate under steady state, so under steady state, this is under steady state operation, this is under steady state operation, okay, so this is undergoing some steady state operation. Now if this is undergoing some steady state operation, let's see what we can talk about. First of all, if you again apply mass balance, you will find out for die air. First of all, if you write it for die air, you have m dot a1 plus m dot a2 will be equal to m dot a3 actually, correct? This is m dot a3. For water vapor, mass of vapor entering to section 1 plus mass of vapor entering to section 2 is equal to mass of vapor entering to section 3 actually. Okay, now let's see some important things here. This gives you omega 1 times m dot a1 plus omega 2 times m dot a2 is equal to omega 3 times m dot a3 is what you have. But this m dot a3 can be replaced with some of these two, so I am just erasing this and writing it as m dot a1 plus m dot a2 actually here. Okay, and if you know these two quantities and these two inlet conditions, you can calculate what is omega 3 from this equation. Okay, also if you slightly adjust the terms in this equation, you will see omega 1 minus omega 3 times m dot a1 is equal to omega 3 minus omega 2 times m dot a2 actually here. So this tells you m dot a1 by m dot a2 is equal to omega 3 minus omega 2 divided by omega 1 minus omega 3. Many of you will be struggling to see these formulas and all, but you see how simply they are getting. Okay, just I'm doing divisions and additions in this case. Okay, so this formula is generally a bit important. And also try to see one more thing. I want to show you this. Correct, so this formula is correct, 1 2 3 of this. Then if you shift this m dot a1 term here, omega 1 minus omega 3 is equal to omega 3 minus omega 2, and this by this is equal to this by this. Fine. Now if you do energy analysis, let's say energy analysis or energy balance, you can say mass balance you applied. So if you apply energy balance, clearly this is insulated. Okay, so this device is actually insulated and there is no amount of work interaction. And potential energies and kinetic energies if you neglect, because you know it's like kinetic energies will be very small as compared to the enthalpy values. Now in energy balance, or let us do this energy balance in the next page better. if you do energy balance actually in this case, okay, now enthalpy coming in should be equal to enthalpy which is leaving out because it's under steady state. Now what is enthalpy coming in? m dot a1 h1 plus m dot a2 h2 is equal to m dot a3 h3, correct? So this is what we have. Now clearly this implies m dot a1 h1 plus m dot a2 h2 is equal to m dot a1 plus m dot a2 times h3 actually. If you again write this ratio of m dot a1 by m dot a2, let's see what you will get actually, okay. M dot a1 times of h1 minus h3, so that comes in the denominator here, is equal to h3 minus h2. That's what you have, okay. So from this equation, this is also a ratio of a1 by a2, and this is also a ratio of a1 m dot a1 by m dot a2. So if you call this equation 2 and this equation as equation 1, then you can understand from 1 and 2, from 1 and 2 you have m dot a1 by m dot a2 is equal to, now this guy, omega 3 minus omega 2 by omega 1 minus omega 3 is equal to this expression h3 minus h2 by h1 minus h3. That's it, okay. So this is what you have actually here in this case, and this formula some of you might have already seen in case of adiabatic mixing, okay. How many of you have seen this formula in case of adiabatic mixing? In normally in any, if you take any thermodynamics or applied thermodynamics textbooks, you will see normally adiabatic mixing. But see, whatever the process they give you, simple basic thermodynamics has to be known. If you know simple basic thermodynamics, apply continuity, so this is continuity, and apply energy balance, you will get the equation. And this is basically from your steady flow energy equation, okay. Q is 0, W is 0, delta K, delta P is 0, then delta H has to be 0, H inlet has to be equal to H outlet. That's it, okay. Clear to all of you? And if you want to show this process on a psychometric chart, let's see. Adiabatic mixing normally, if you talk about the case of adiabatic mixing, so let's see. This is the psychometric chart. T dye bulb temperature in degrees Celsius. Then this is your omega, maybe kg of vapor per kg of dye air per kg dye air, okay. So this is kg of vapor per kg of dye air. Now let's say if your state 1 is somewhere here and state 2 maybe at some different temperature here, when you mix these two, they become to some equilibrium condition, okay. So the properties and temperature will be somewhere in between. So let's say this is state 1 for example, and this is state 2, and this is your state 3 actually, okay. So state 3, because these two samples got mixed and they got to certain equilibrium temperature and also some equilibrium omega. Let's say for example this is having high omega and this is having low omega, then after mixing definitely they have some intermediate omega and also temperature. If you now see one thing carefully, this point here, sorry, yeah, something like this, okay, and this point here and this point here, similarly, okay. So this is what you have. And also if you take the enthalpy scale, okay, so if you for example take your enthalpy scale, say something like this, then so see carefully, okay. So let's say enthalpy scale is going forward, okay. So this is your enthalpy 3 at this state, and this is your enthalpy 2 at this location, okay. So this is enthalpy 2, of course. Now see something very interesting. This value corresponds to omega 3, this value corresponds to omega 2, and this value corresponds to omega 1. Similarly, this value corresponds to H1, this corresponds to H3, and this corresponds to H2 on this enthalpy scale, okay. So this is your enthalpy scale. Now try to get something here. This difference, this height difference in this diagram is nothing but omega 1 minus omega 3, correct. And what is this height difference here? We have omega 3 minus omega 2, And what about this difference? This difference is nothing but your H1 minus H3, and this difference is something like H3 minus H2. Okay, so this is what you have. Now tell me one thing. This length is nothing but projection of this, and this length is nothing but the projection of this about this axis. Okay, means if you see, we might have seen in case of hydrostatic forces. Okay, in case of plane surfaces, if you have a plane like this, then the projection of this element onto this is this height. So by projections, if you see geometrically something here, okay, so normally I have two streams at two different conditions and they got to some equilibrium state at 3. If from geometry you can understand one thing, since this is proportional to this and this is proportional to this, then definitely omega 1 minus omega 3 by bottom term omega 3 minus omega 2, this is same as omega 1 minus omega 3 corresponds to H1 minus H3 divided by H3 minus H2, correct? And this ratio is same. Of course, if you interchange both these fractions, you will get this. Okay, so this is from psychometric chart in geometric point of analysis, and this is mathematically from your steady flow energy equation and also this continuity stuff. Understood? So is this clear to all of you? Yes or no? Come on, type in the chat box. Can you understand what is the geometry that's happening here? So just from projections, this equation is same as this equation. Okay, fine. And this side corresponds to this m dot a1. So by lever rule, you can see m dot a1 by omega 3 minus omega 2 is equal to m dot a2 by omega 1 minus omega 3. So if you simplify these two, like if you put this here and if you put this here, this about this point, like you have the lever rule actually in case of iron or basically phase diagrams. About this point, if you take the levers, this is 2. So m dot a1 by omega 3 minus omega 2. So you can see m dot a1 by omega 3 minus omega 2 is also same as m dot a2 by omega 1 minus omega 3, m dot a2 by omega 1 minus omega 3. Similarly, you can also do the enthalpy analysis. Okay, so basically we can calculate the properties of the mixture by the help of the lever rule at this point. Okay, see, basically what I am telling Nitin is, see here, if you project this length on omega axis about this line, see this is the reflection line. So if you project this omega about this line onto enthalpy, this H1 minus H3 means this length is nothing but the projection of this length. Okay, similarly this H3 minus H2, this length is projection of this omega 3 minus omega 2. So that's what I'm telling. Can you understand this? You can also do this with the help of lever rule, that m dot a1 by m dot a2 is equal to one of these two quantities. Okay, fine. So every one of you, please type in the chat box. Is this clear to all of you? Nitin, Pritam, Vivek, Sukumar, Yogesh, Loha, Beam, Sukumar, Ankit, Pavat, Chetan, every one of you. Right? Yes. Okay. Now, so with this we conclude this chapter. Of course, still we can see if I want to we have a lot of process, other process and all. But anyway, the story is same. Just apply steady flow energy equation and also this stuff, mass balance. That's it. Okay. And in GATE examination, things didn't go beyond this as well till now. Okay. But even if they ask you, you can just apply this energy balance and mass balance. You will get answers easily. Okay. Now let's see. We have some problems before going for compressible flows. Yeah, this is compressible flows. Fine, we'll go. But come on, solve this question. Solve this question. Actually, solve this question. I'll conduct a. Wait. Is there anything that I can do? Humidity ratio of the final stream. Okay, so I think I cannot conduct a poll because vote type is not there. So anyway, I'm giving some 120 seconds, but what you will enter? Okay, so let's say if you got your answer 0.001, something like that, you enter the first two digits as integer value. Okay, means let's say if my answer is 0.024 something, enter your answer as 24, or 0.01716 something like that. You enter 17 or 16 as the answer, depending on rounding off to 3 decimals. See, after rounding off to 3 decimals, if this is the value, enter your answer as 17 here. Start. Round off to 3 decimals, then whatever the value you get, enter that as integer in this chat box. Okay, come on, do this question. A stream of moist air, mass flow rate is 15 kg per second, with humidity ratio of 0.01 kg per kg of the air, mixes with second stream of superheated vapor, water vapor flowing at 0.1 kg per second. Assuming proper and uniform mixing with no condensation, the humidity ratio of the final stream is dash. So these two streams, one is moist air and one is water vapor. These two guys are mixing. Then what could be the conditions of the final air stream? That's the question. Come on, do this. Come on guys, the time is running up fast. Done? You are able to solve this? Come on guys, it's already 1 hour since we have started. Only 1 more hour left. Fine. Okay. So see here, I'll solve. There is a stream like this. Okay. Now let's see. Through this we have m dot a1, and this is only vapor is flowing. So let's say this is m dot v. Okay. So this is m dot v. Then you have the mixture at these conditions. So what they're asking you, look, the humidity ratio, which is nothing but omega. Okay. So humidity ratio is omega. So omega of the final stream, 14 or 16, something like that is coming. Okay. Let's see. Now if you apply mass balance, mass balance gives you m dot a1, and here there is no atmospheric air. I mean, here there is no dry air. It's only a complete stream of water vapor. So this is same as m dot a3, which is m dot a. That's what you have. Okay. Because you see here there is no air which is flowing. It's purely water vapor. Correct? They told you it is second stream of superheated water vapor flowing. Okay. So this is complete water vapor. There is no air which is flowing here. Now if you apply vapor balance, here, then let's see, m dot v1 plus this m dot v should be equal to vapor present at the third state, m dot v3. Okay. So m dot v3 actually. So what is m dot v1? Omega 1 times m dot a is what we have, plus m dot v is equal to omega 3 times of m dot a is what you have, because this m dot a1 and m dot a3 are equal, and that's equal to m dot a actually. Now let's see what we can do. If you delete this m dot a all over, m dot a actually, omega 3 is equal to omega 1 plus the ratio of these two. Okay. So if you do this, omega 3 is equal to omega 1 plus m dot vapor by m dot air, actually here. Okay. So this gives you omega 3 is equal to, what is omega 1? They might have given omega 1 is 0.01 kg per kg of dry air, plus mass flow rate of vapor is 0.1 kg per second, 0.1 divided by mass flow rate of air. So this is 15 kg per second of air is actually entering. So this is 15. That's it. So omega 3 will be some amount of kgs per kg of dry air actually. Okay. Per kg of dry air. And what are the units they're asking? Kg per kg. Okay. So correct up to 3 decimal places. Fine. Let's see. 0.1, 0.01 plus 0.1 by 15 is what you have. Okay. So 0.0166, 0.0166. So this is equal to 0.017 kg per kg of dry area. Guys, this rounding off is a bit important. Okay. So please look at this. So this is actually a omega 3. Okay. So this is your omega 3. Yeah. 0.0166. Clear? That's the answer. Got it? So maybe some of you might have entered 17. Let's see if some of you have entered 17. I know some of you might be entering 16 also because we don't have decimals here. But yeah, anyway, I understand. Some of you might have entered it as 16, things like that. Okay. But this is the correct answer. 0.017 means it's roughly like 16.66 grams of vapor is present in 1 kg of dye air. Okay. Yeah, 16 you have entered. Okay, fine. No issue. It's okay. I understand because I cannot check it for the decimals at the chat box. Okay. So fine. So is this clear to all of you? See, whatever the question they give you no need of any panicking at any point. Okay, if it is a theoretical question, just draw the psychometric chart, try to see what's happening. Okay, if I increase the temperature, if I increase omega, then what happens to phi, what happens to humidity, all these points you just think. Okay, guys, actually answering theoretical questions is very, very easy if you have strong conceptual background. Okay, definitely you might have seen before I start applied thermodynamics, many of you might be by hearting the points of effects of regeneration or effects of this reheating in Brayton cycles, Rankine cycles, all this stuff. Okay, and in this psychometry. But now I hope you got enough idea. If something is given, just go for the mathematical analysis and then try to answer. Okay, so is that clear to all of you? Yes or no? So please type in the chat box. Is this clear to all of you? Okay, now so let's solve one more question which I have options I got with you, so you can solve this maybe. So this time I'm giving a single choice question. It's a MCQ. Okay, so it's a MCQ. That's the psychometric chart, and you see, find the mass of water added from air at 15 degrees Celsius and 80% relative humidity to temperature of 25 degrees Celsius and relative humidity of 50% if volume supplied to the space is 2.4 cubic meters per second with specific volume of 0.8 meter per kg of dye air. Come on, solve this question. Single choice. So what you have to find? If volume supplied of the space is 2.4, fine. Okay, fine. So 120 seconds I'm giving. Start. Okay, Sujay. Yep. Come on, solve this. There is some amount of air which is there. To that air, we are doing some dating. We are adding mass of water added. Okay, so we have added some water so that it properties change. Okay, so they are asking what is the amount of water added. See, these values are given to you. This is 0.01 and this is 0.0086 kg of vapor per kg of dye air. Okay, yeah, roughly 10 grams. That's it. Come on, guys, the time is running up fast. Okay, yep, done. Come on, quick. Maybe this can be a 1 mark question in GATE exam. Okay, so anyway, let's see. Fine. So see here. Basically what they're telling you, look, find the mass of water to be added from air at 15 degrees Celsius and 80% relative humidity. So you can see initially there is air at this point, 15 degrees Celsius and 80% relative humidity, means this is the point. So this is the state 1 of the air because this is at 15 degrees Celsius and also 80% relative humidity line. For this, some water is added at 25 degrees Celsius and relative humidity of 50%. So what happened? So because of addition of some hot water, what happened? Heating with humidification happened and this state went to here where it is 25 degrees Celsius and also basically this is 50% humidity. Okay, so definitely it's like heating with humidification. That's it. Okay, so heating with humidification, because point goes from 1 to 2. It's increasing temperature and also it's going in increasing of specific volume. If the volume supplied to the space is 2.4 cubic meter per second with specific volume of 0.8 meter cube per kg, fine. So let's see, they're asking what is the amount of water vapor added. We all know in case of this heating with humidification, see in this process, I have told you, see here, somewhere here, m dot f is nothing but omega 1 minus omega 2 times m dot a. Of course, this is dehumidification, fine. So in case of humidification, you can see omega 3 minus omega, of course, if you have only two states, let us see. If you have only two states like this, okay, so if you have only two states, m dot f is equal to omega 2 minus omega 1 times m dot a is what we have here, correct? So this is nothing but the amount of vapor which is, or water which is added. So m dot f is equal to omega 2. So omega at this state, at second state, they have given directly psychometric chart. So this is omega 2, 0.01 minus, what's omega 1? Omega 1 at that point, 0.0086 times m dot a. So this mass flow rate of air can be written as volumetric flow rate by specific volume, correct? I can do that. So m dot f is equal to 0.01 minus 0.0086 into v1 dot. So total amount of air which is supplied is 2.4 cubic meter, okay, and this is also in meter cube per kg. So this is 0.8 actually, and this value is 3. So if this is 3, this value is going to be in kgs per second. So if you convert, we'll get into grams per second. That's it. Okay. So 0.01 minus 0.0086. So this value into 3. That's it. 42. 0.0042. 0.0042. So 4.2 grams per second of air is actually sent inside. I mean water vapor is actually added. Okay. Yeah, 4.2. C is the correct answer. You're getting 3.6. Why? Why 3.6, guys? Any any calculation mistake that we have done? Yeah, 4.2 grams is correct, I guess. Okay, because you see it's a simple calculation, nothing to worry much in this. Okay, fine. 4.2. So C is the correct answer. Yeah, C is the correct answer basically. So C. Sorry, forget to divide by 0.8. That 0.8 if you don't divide, then then your value will be much below. No, it should be something like 1.6, I guess. Fine. Anyway, C is the correct answer. Why? Poll did not work or what? Poll is not working. Okay, let's see. Fine. So we have two more questions which you please work out by yourself. Okay, so I'm starting this compressible flows. Okay, so compressible flows. Fine. Okay, taken more time, but it's a simple calculation. No? It would have taken only 1.5 minutes if you have solved by yourself. Okay, fine. So shall we start compressible flows now? The last chapter of this subject. Actually, I was supposed to cover this in fluid mechanics part, but there we did not find enough time, so I'm taking it now. Okay. Are you all ready for this compressible flow? Shall we start this? Okay. Now, so let's see. Before starting this compressible flow, going directly for the stagnation and sonic properties, let us see what is a compressible flow. Compressible fluid and compressible flow, the wording between these two. I think I have told you during this bulk modulus part, okay, in fluid mechanics. So we know E, normally if you take this bulk modulus, this is minus dP by dV by V actually here, okay, and clearly depending on isentropic or isothermal, we'll have isothermal bulk modulus and isentropic bulk modulus. Okay, FM and DDT compressible flows are same only. Basically, see guys, I'm telling you, in complete fluid mechanics, whatever I taught you, we have never taken the heat interaction which is coming in. Okay, but normally if heat is coming inside, then definitely that's actually the thermo fluids. Okay, so heat comes in, then definitely fluid flow will get affected. That's what your heat transfer is. Depending on the transfer of heat, the fluid actually moves in a particular fashion. Clear? So that's what we are studying here. Okay, now if you see, this is basically in two cases, isothermal and also adiabatic bulk modulus, and normally we are talking about adiabatic bulk modulus in this case. Okay, so let's say this is adiabatic isothermal depending upon constant temperature or constant entropy here. But to whether if E is high, if E is high, then fluid is highly incompressible. Highly incompressible. Because it tells you that if this dV, let's say for example I have some amount of substance, okay, so I got some amount of substance. If I want to decrease the volume of the substance by 1 unit, say my dV is actually 1 unit, okay, so let's say if I want to compress this substance, if I want to change its volume by 1 unit, to change this volume by 1 unit, if dP has to be very high, okay, so let's say if this is the case, if E is very high for compressing the substance, that means I feel it very difficult to compress the substance, yes or no? So those substances with high values of E are called incompressible substances. And in case of this compressible flows, you can see practically what happens is, I have told you scaling analysis, okay, so if you take these two sections, section 1 and section 2, normally what happens, order of change in pressure between the two quantities will be of the form order of rho v square by 2 actually here, okay. So this scales to that value. Normally if you see Bernoulli's equation, P by O plus V square by 2 is equal to constant, that's what you have, okay. So P by O is equal to constant minus V square by 2. So this del P will be of in magnitude, maybe 2 times or 3 times depending upon the scaling. So this del P will be of this magnitude, rho V square by 2, and del P in this pressure change in any fluid can be written as, this formula can also be written as E is equal to dP by d rho by O, because if you take any mass of any substance, rho v is equal to constant actually, and if you do differentiation, we'll get d rho by O plus dV by V is equal to 0. So this gives you minus dV by V is equal to d rho by rho actually here, okay. So because whatever is the amount of fluid you take, whatever the pressure change or whatever you subject to it, definitely the mass of the substance has to be same, okay. So therefore mass is equal to density into volume, which is constant, so this gives you this. So therefore this term with this minus sign can be replaced with a plus sign and dO by O. So this dP can be written as E times dO by rho actually here. So that will be of the scale rho v square by 2 actually, okay. So that's what we have the scaling actually here. dO by O is proportional to rho v square by 2 actually, okay. And you will understand later, not readily, but sometime later you will understand E by O scales to something called acoustic velocity, root E by O, okay. So root E by O, normally this adiabatic bulk modulus, let's say this is adiabatic bulk modulus by density, we are talking about adiabatic conditions, no heat flow. In case of adiabatic conditions, this scales to acoustic velocity, which is nothing but velocity of the disturbance in this medium. Means let's say if a sound wave start traveling in this medium, then what is the speed at which this sound wave move in this medium is called this acoustic velocity. And you clearly see this Es by O, if I cause this as acoustic velocity times d rho, this is proportional to rho v square by 2, and d rho by O is proportional to, so this is square, a square, okay, because a is square root of this value, so this value is a square. This scales to v square by 2 times of a square, okay, and this is equal to 1 by 2 times of v by a whole square. So this quantity is nothing but a dimensionless quantity, because this is a ratio of 2 values, actually 2 velocities, okay. So first velocity is the actual velocity of the fluid, and second velocity is the velocity of this disturbance in this medium, okay, in this fluid. So this v by a is actually called Mach number, clear. So v by a, where v is actual velocity of the body or maybe fluid, you can say actual velocity of some body in the fluid, and a is the acoustic velocity, or let's say of some fluid, of some medium, let's say of some medium, it may be gas or liquid, whatever, acoustic velocity in the medium, acoustic velocity in the medium actually, okay. If this is the acoustic velocity, then this v by a is a dimensionless quantity, and this dimensionless quantity is actually called Mach number. Because this analysis of compressibility was done by majority with this person, Ernest Mach. So this is normally called Mach number. Okay, so if you want to decide whether a flow is incompressible or not, see, if you want to decide whether a fluid is incompressible or not, you will see this bulk modulus value. If bulk modulus is very high, fluid is highly incompressible. If bulk modulus is very low, then definitely fluid is easily compressible. But in case of this fluid flows, what happens here is, see, because of this pressure change, let's say here the pressure is P1 and here the pressure is P2. Because of this pressure change, let's say here the pressure is less, okay, and here the pressure is P1 actually. Then definitely, because of this pressure difference, this fluid which is lying in between, so this fluid which is lying in between will be subjected to some pressure. Yes or no? Can you understand? Because of this pressure difference P1 and P2, the fluid which is in between will be definitely subjected to some pressure actually. Correct? Yes or no? Type in the chat box. Can you understand this? Because of this pressure difference, this fluid which is in between these two sections will be subjected to some pressure difference, P1 minus P2. Clear? Yes? Yes. So this fluid gets compressed actually. Now, let's say if this P1 minus P2, which is nothing but this delta P, is very high, then this fluid for high delta P, fluid experiences compressibility effects. Fluid experiences compressibility effects actually here. Okay, so fluid experiences compressibility effects. Now let's see, in this case, because if this is Mach number, I can write this as d rho by rho will be scaled to half times Mach square. Okay, now this quantity which is here gives you fractional change in density, or you can say a relative change or fractional change, you can say a relative change in density. Yes or no? Can I say this? Because this dO by rho gives you what is the relative change in density of the fluid under subjected to this pressure. Compressibility effect means just basically it undergoes the effect of this compression from the fluid. Okay, that's it. So now if you see, now what we do is, one thing is very clear, depending on this pressure difference, this fluid undergoes certain compressibility, or basically it undergoes certain compression. Now if the compression is such that the density variations, because if you want to decide something is getting compressed or not, definitely density is the one very important factor. So because of this compression, if density of this fluid is not changing more than 5%, then we treat that as incompressible flow. Means if dO by rho is less than 5%, then flow is incompressible. We say flow is incompressible. And I forgot one thing, this is also called sonic velocity. Sonic velocity means Mach number is equal to 1 at this point. Okay, because if the object is moving at this a, then Mach number is equal to 1, and this speeds at which the body moves at the disturbance speed is called the sonic velocity. And anyway, if you see here, if this density variations are less than 5%, then the flow is incompressible flow. Okay, if density variations is less than 5%, this implies half times, because these two scales each other, Mach square less than 0.05. Yes or no? Because this is 5%, so 5 by 100, 0.05. Mach square less than 0.1, so Mach number is less than, if you take square root of 0.1, then let's see, 0.1 square, 0.1 square root, 0.316, and some books they round it off as 0.3 to 1 decimal, or some books they write it as 0.32, 0.33, sometimes people write 0.33, because this is 1 by 3, easy to do calculations and all. So that's why any flow which is generally Mach number less than 0.316, which is in this Mach number less than 0.316 means the density variation in the fluid because of the pressure difference applied in the flow is less than 5%. Okay, so in such cases we treat the flow as incompressible flow. Did you all understand? So for Mach number less than 0.3, we call this incompressible flows, which we all do in our fluid mechanics analysis. incompressible flows. This is incompressible flows. Okay, like we have seen in our fluid mechanics, normally what they say, they'll say you the pipe has a velocity of, the fluid in the pipe is flowing at 30 meters per second, 40 meters per second. If you calculate for 30 meters per second, 40 meters per second for liquid water, this value will be something like 0.04, something like that. Okay, so that's why we always take, when we are doing density analysis, when we are doing Bernoulli's equations and all the stuff, we take density out as constant, because from this section to other section, density do not vary in between. Clear? Did you understand? But in this case, we will talk about the story which is after this 0.33. Okay, maybe Mach number 2, 2.4, 1, 1.8, 0.8, things like that. Okay, is this clear? Did you all understand the different regimes of the flow? One is incompressible, where Mach number is less than 0.3, and one is more than 0.3, which is supersonic. This we'll see compressible flows basically. For Mach number lying between 0.3 to 0.8. Since this is sonic, okay, so this is called subsonic flows. Subsonic flows. Okay, normally your aircrafts and all, they flow within this region. Okay, and for 0.8 to 1.2 roughly, they call this. Here you can see there is a transition from this subsonic to supersonic, so we call this as transition flows. Transition flows, like how you have a transition between laminar to turbulent, here we have the transition from subsonic to supersonic. For normally 1.2 to Mach number less than 5 up to 5, we call this supersonic flows. Supersonic flows. And for normally, let's say your Mach number is more than 5, we call it hypersonic. Hypersonic flows actually here. Okay, so this is, and all these are categories under compressible flows, because Mach is definitely more than 0.3 in these cases. Okay, so is this clear to all of you till this point? So basically, if you want to decide whether a fluid is compressible or not, you will check this bulk modulus, and if you want to check whether a flow is incompressible or not, you will check the Mach number of the flow. Understood? Okay, did you understand this? If you want to check whether a flow is compressible or not, you should check Mach number. If Mach number of the flow is less than 0.3, then it's incompressible. If something more than 0.3, then we'll see out of this which is the case. Okay, fine. Now, so is this clear to all of you? Everyone, so please type in the chat box. I think few of you are busy in taking notes, but anyway, notes will be uploaded, but right now just be focusing, okay, on the stuff what I'm telling you. So this is hypersonic flows. Now our preliminary job is, we have already seen this guy in fluid mechanics. Okay, so this is already addressed in fluid mechanics. In our at level, actually this complete is fluid mechanics, but we have already seen this. Now our job is to talk something about these guys. Okay, now so we will talk about some important things which is called stagnation properties. Stagnation properties. So what is a stagnation point? We know the stagnation point is the point where the flow is locally having a velocity 0, correct? So let's say, for example, if there is a submarine, something like this, then you all know at this point, somewhere close to this, we have a stagnation point. Stagnation point. So this stagnation point is basically the point where local velocity of the flow, is 0, correct? So this is stagnation point. Now what are stagnation properties? Are nothing but the properties at that particular state of the fluid. Okay, so let's say there is some gas, for example, or maybe some liquid, whatever, some fluid is there. So at this point of stagnation, what is the pressure, density, temperature, specific enthalpy, all these things we call it as stagnation properties. Stagnation pressure, stagnation temperature, stagnation enthalpy, things like that. Okay, now let's see few important things here. If there is a fluid which is flowing like this normally, by the time we brought it here, it touches a velocity 0. So let's say at this point it has a stagnation temperature Ts, and at somewhere in the upstream its temperature is T, and this is flowing with a velocity V, and here the velocity is 0 actually here. Okay, and let's say if you are talking about gas, for example, for easy analysis, if there is a gas which is flowing like this, then this T will convert to Ts temperature, and here this gas also has certain kinetic energy which is V, and here this gas don't have any kinetic energy, it is 0 actually. Okay, so stagnation properties, the properties of the fluid, when the fluid is brought to rest, isentropically or adiabatically, you can say, normally adiabatically means from this fluid, see this is adiabatically, and normally if you see, so at this point, if from this point if you can bring this fluid to rest without making this particle lose heat to surroundings, then we say the properties at this point are called the stagnation properties. Okay, now if you apply energy of conservation again, see here, you can understand at this point the total energy available with the fluid particle is enthalpy, because it has got some temperature, plus V square by 2. Yes or no? So this is the kinetic energy for a particle. Yes or no? If there is a particle at time T, and if there is a particle at temperature capital T, and also if this particle is moving at a velocity capital V, then definitely if you bring this guy to rest adiabatically, then definitely you can understand if this is V here and if this is 0, at this point 1, the energy available with the fluid particle is, because of this temperature it is at some enthalpy, and because of this velocity it has got some kinetic energy which is H plus V square by 2. Yes or no? And this is equal to, finally when the particle reaches here, it has only temperature but no velocity, so this is stagnation enthalpy actually. Okay, so HS is stagnation specific enthalpy. Okay, so this is stagnation specific enthalpy. Now clearly you can see for ideal gas, let's say if this is ideal gas, if this substance is ideal gas, for ideal gas you can see H is equal to Cp into temperature, we know this, so this gives you H can be written as Cp into T plus V square by 2 is as usual is equal to Cp into Ts. Now if you want only stagnation temperature, then what you can do, you can divide this Cp all over in this equation, so we get Ts is equal to T plus V square by 2 Cp actually here. Okay, so this guy gives you V square by 2 Cp, of course this is the equation. So the stagnation temperature means the temperature at that point for this particle will be Ts, which is equal to T plus this kinetic energy completely gets converted to heat, and that heat cannot escape obviously, so that will lead to further increase in temperature of the particles, which is called as T, which is actually here, plus V square by 2 Cp. This V square by 2 Cp is the quantity of temperature which got converted from kinetic energy to heat actually. Okay, so this quantity V square by 2 Cp is called, since this is because of the movement of the particle, this is called dynamic temperature. This is called dynamic temperature, and this is how we calculate Ts actually here. So is this clear to all of you? Are you all clear till this point? Did you understand how we have calculated the stagnation temperature, Ts? So let's say if there is some flow of fluid at a velocity V, then this is how we calculate the stagnation temperature because of this understanding. Okay, because you can clearly understand if you take a small control volume, you can understand here, if I take a small control volume like this, then definitely you can understand at this point there is no heat which is insulated because I am bringing it adiabatically to rest, no work, nothing. So this complete energy should be equal to complete energy here, that if I equate, this is what we will get. Okay, now let's see, since Mach number, because it's always important for us to write in dimensional form, V can be written as A into ma actually. Okay, so acoustic velocity multiplied with Mach number. Okay, so this is acoustic multiplied with Mach number. Therefore this implies Ts is equal to T plus T plus V square by 2Cp is what you have. Okay, so V square by 2Cp, if you see V square, so V square can be written as A square MA square divided by 2 times of Cp actually here. Okay, so V square T plus V square is nothing but A square MA square divided by 2 times of Cp is what you have here. Okay, now let's try to understand something here. What is this A square by Cp? That's the main important condition. We will see later. I'll show you maybe in the next part. Yeah, acoustic velocity here I'll show you, but as of now I'm giving you, you might have seen acoustic velocity for ideal gas. For ideal gas, I'll show you this how this is coming, but you might have seen this already, square root of gamma RT. Have you all seen this? Where R is the characteristic gas constant, T is the absolute temperature. Have you seen this before I do the derivation? Anyway, I'll do the derivation today itself, but just tell me, A is equal to square root of gamma RT. Have you seen this? Root gamma RT is nothing but your acoustic speed. I think 2022 gate question also in mechanical, this formulation. Okay, fine. Yeah, now let's see if I do this as A square is equal to gamma RT, then this term becomes Ts is equal to T plus A square, you can be written as gamma RT into max square divided by 2 times of Cp actually here. Now what is R by Cp? This quantity. We all know Cp minus Cv is equal to R and Cp is equal to R plus Cv. What is Cv? R by gamma minus 1, correct? So Cv is actually R by gamma minus 1, Cp is gamma R by gamma minus 1, just basic thermodynamics, just float it out here. So R times of gamma minus 1 plus 1 by gamma minus 1. So this gives you the quantity which is something like R times of gamma upon gamma minus 1 actually here. Okay, so Cp by R talks something about gamma upon gamma minus 1 actually here. Okay, so gamma upon gamma minus 1, because Cp is equal to R plus R by gamma minus 1. So R, if you take out gamma minus 1 plus 1 by gamma minus 1, 1 gets cancelled. Fine. Okay, so this is the equation. Now if you write this here, Ts is equal to, if I take this T common in both quantities, I have 1 plus gamma by 2, this gamma by 2 is as usual gamma by 2 into this R by Cp. Okay, so we have R by Cp, so gamma minus 1 upon gamma actually. Okay, because this is R by Cp, here this is Cp by R. Okay, so multiplied with Ma square is what you have. Now clearly you can see this gamma and gamma gets cancelled. So saturation temperature, sorry, stagnation temperature by temperature is equal to 1 plus gamma minus 1 by 2 times max square is what we have here. This formula you might have seen in many of the books, that this is the condition for stagnation temperature, and if there is a medium at temperature T which is flowing at Mach number, say some Mach number 0.2, 0.4 or maybe 3, 5, whatever, stagnation temperature can be calculated with this property of the fluid gamma and also this Ma square actually. Okay, so this is your condition, and we know in first class I was talking gamma is equal to 5 by 3 for monoatomic gamma, 5 by 4, no, 4, sorry, it is 1.4, right? So 1.4 is 14 by 10, 7 by 5. Yeah, for diatomic, and gamma is equal to 4 by 3 for triatomic gases. And in case of diatomic, we have oxygen, nitrogen, air, all of the stuff. Okay, so this is how we can calculate this properties. Okay, so this is Ts by T, which is 1 plus gamma minus 1 by 2 max square. Okay, so if you now see how to calculate the stagnation pressure and all, stagnation pressure, stagnation density maybe. Okay, so let's see how we can do that. So this is the story of stagnation temperature. For stagnation pressure, actually. Okay, so stagnation pressure, if you need stagnation pressure, okay, sorry, didn't get you, sir. Tell me, Nitin, any doubt till this point? Guys, tell me till this point, is there any doubt to anyone? Till this point, if do you have any issues? So please type in the chat box. Any issues till this point? Just a minute, yeah, please take, I'll have some water and come back. Yeah, any issues till this point? All clear? Yeah, no issues, right? Good. So let's see now stagnation pressure. Since if I call this point as 1 and if I call this point as S, you know 1 to S is isentropic. Of course it is reversible only, we are not taking any irreversibilities as of now. In reality there are certain irreversibilities, you have correction factors, but let's say in this GATE syllabus we have only isentropic case. Then we know P1 power 1 minus gamma into T1 power gamma is equal to PS power 1 minus gamma into TS power gamma actually. So PS is equal to P1 times of, so PS is equal to P1 times of T1 by TS whole power gamma upon 1 minus gamma actually. So this tells you PS by P1 is equal to TS by T1 whole power gamma by gamma minus 1 is what you can say. So PS by P1 is equal to, what is TS by T1? This is the equation, 1 plus gamma minus 1 by 2 max square power gamma upon gamma minus 1 actually here. Okay, so this is the expressions for static pressure, stagnation pressure divided by the actual pressure. And also if you talk about densities, we know since P1 power rho 1 power minus gamma is equal to P2 power rho 2 power PS into rho S power minus gamma, because PV power gamma is equal to constant, V is 1 by density, small v I'm talking, okay. So P into specific volume power gamma is equal to constant, so that can be written as rho power minus gamma because rho is 1 by V, okay. So this gives you stagnation density is equal to rho 1 times P1 by PS whole power minus 1 by gamma actually, okay. So this is what we have, because 1 by minus gamma is what you have, P1 by PS whole power 1 by minus gamma, so minus 1 by gamma. Rho S by rho 1 can be taken as PS by P1 whole power 1 by gamma then, okay, because you can see this minus sign, if you want to eliminate, A inverse is 1 by A, so if I flip this then I can put this as positive sign. So rho S by rho 1, these are the stagnation properties. PS by P1, so what is PS by P1? Here you got this 1 plus gamma minus 1 by 2 max square power gamma upon gamma minus 1, this whole power gamma, 1 by gamma, okay. So you have this 1 by gamma, this gets cancelled, so stagnation density by density of the flow is equal to 1 plus gamma minus 1 by 2 max square times of 1 by gamma minus 1 actually, okay. So this is how we talk about the stagnation densities actually here, okay. So that's how we calculate. Okay, this little fellow is not going, but you can think that this is the relation for calculation of stagnation temperature in terms of gamma and Mach number, and this is stagnation pressure in terms of gamma and Mach number, and of course P1 is known to you, and OS is calculation of this. Now why I'm very much interested in calculating this, guys, is we'll be in need of these calculations when we're talking about shocks and other stuff, okay. So this is what you have. Now let's see what are sonic properties. Sonic properties, property, what is spelling of property? Sonic properties, yeah, this is sonic properties. So basically sonic properties are nothing but the properties of the fluid, when it is flowing at, when the fluid flows at Mach is equal to 1, okay. So that's basically the sonic condition. So at Mach is equal to 1, and properties are denoted with symbol star on the top, okay. So sonic properties are denoted with star on superscript, superscript means something like you'll have T star, P star, rho star. This is how you actually denote. Okay, and the area of the flow at that particular point is noted as A star normally. Okay, we'll see in case of converging nozzles, maybe in tomorrow's class we will touch upon that. So now if you see this, so we have this implies, now again if you do the same story for this, since Ts by T star is equal to, so Ts by T star is equal to this relation 1 plus, sorry, Ts by T is equal to 1 plus gamma minus 1 by 2 max square. This is what we have. Now if you see at this point, if Ts is equal to T star, then definitely Mac is equal to 1. Okay, so at Mac is equal to 1, this Ts will be actually T star at this point. So T star by T, if you put Mach number is equal to 1 here, 1 square is 1, so 1 plus gamma minus 1 by 2, so this is gamma plus 1 divided by 2 actually here. So sonic temperature by this T is equal to gamma plus 1 by 2, gamma plus 1 by 2, and this value, okay, so let us keep it this way. This is gamma plus 1 by 2, means here if you put this Mach number is equal to 1, we will end up with gamma plus 1 by 2. So therefore, if you try to do P star by P is equal to, so let's say if the gas is flowing at temperature T, then the sonic temperature of the gas is gamma plus 1 by 2 times this T. Similarly here P star by P is equal to, see this is P star, Ps by P1, so P star by P is equal to, if I put gamma Mach number is equal to 1, I have 1 plus gamma by 2, because this temperature after solving, this is what you will get, whole power gamma by gamma minus 1, so gamma upon gamma minus 1, and rho star by rho is equal to, so again in this case this value is gamma plus 1 by 2 power 1 by gamma minus 1, 1 by gamma minus 1 actually here. Now if we are talking about air, okay, so for air, since gamma is equal to 1.4, this implies your T star by T is equal to, so guys I am telling you, on 7th you have ISRO exam, this is very much important. Okay, so what are the sonic properties I am writing now, all these things, and also this chapter of compressible flows is definitely important. Okay, so you will tell me definitely after ISRO exam you will definitely see questions from this chapter. Okay, because complete rockets they operate in compressible, okay, in compressible, not in compressible, they operate in compressible regime actually. Okay, so T star by T, so if you put gamma plus 1 by 2, this is 1.4, so gamma is 1.4, 1.4 plus 1, 2.4 by 2, so this is 1.2. You might have seen these values, 1.2. Okay, yeah, this is 1.4, so T star by T, sorry, what we are talking, guys, just a minute, T star by T. Guys, just a minute, there is a small error which I have done. T is equal to T star actually, okay, because this is stagnation conditions, so T is equal to T star, so these things are slightly mistake. Okay, Ts by T star, okay, so Ts by T star, Ts by T star, okay, so this is what you have, Ts by T star. Similarly Ps and rho s, okay, so Ps by P star and rho s by rho star. Yeah, sorry, because fluid is actually moving now at gamma is equal to 1, so this is the case. Yeah, so in a shorthand I have written this, but yeah, this temperature is equal to T star actually, and that's how it follows. Okay, because stagnation temperature is always some fixed value at a given temperature. Okay, so this is what we have. Now for air, if you see T star by Ts or Ts by T star is equal to 1.2, this implies your T star by Ts. If you have stagnation temperatures, then 1.2, 1 by 1.2 gives you 1 by 1 point, I guess 0.8 something, so 0.833, 0.833 is this value. Okay, yeah, this is 0.833, correct. Okay, and Ps by P star is equal to Ps by P star, so this guy, this is again 1 plus 1.4, 2.4 by 1.2, 1.2 power gamma 1.4 by gamma minus 1, which is 0.4, so this gives you your P star by Ps is equal to, now let's calculate this and reciprocate this, 1.2 power 1.2 power 14 by 4, 14 by 4. Okay, so this value, now if you reciprocate, 0.528, 0.528 actually, 0.528. And similarly, if you do density calculations, and if you do density calculations, rho star by rho s is equal to, okay, so rho star by rho s, stagnation density, sonic density by stagnation density, if you take 1.2 power 1.2 power 1 by gamma minus 1, so 1 by 0.4, so 1 by 0.4, 2.5 of course. So this value, then flip it, 0.633 is 64 is what you're getting. Okay, so 0.634 is what you're getting, 0.634 actually, correct? We are getting 0.64. Let's do it again. 1.2 power 2.5, 1.2 power, sorry, 1.2 power 2.5, so flip it, 0.69, yeah, 0.64 actually. Okay, so these are the sonic properties corresponding to atmospheric air actually. Okay, so this sonic property is 0.64 times of this stagnation density, this is 0.528 times of this stagnation pressure, and this is 0.83 times of this stagnation temperature actually. Clear to all of you? Okay, so please type in the chat box, is this clear to all of you till this point? Okay, yes, yeah, in the beginning I have written shorthand that I have replaced this, but actually this is the correct idea. Okay, because fluid is moving now, clearly fluid is moving at Mach number is equal to 1, and so if fluid is moving at Mach number is equal to 1, then T is actually T star. Today you're looking smart, maybe the lighting has got engaged, fine, thank you. Okay, so this is sonic properties actually. Okay, so let's go to one very important part, which is acoustic velocity. Okay, so we have to identify what is this acoustic velocity, and you know, we have to talk certain things. Look, acoustic velocity is nothing but speed of disturbance in the medium at a given condition. In the medium at the given conditions, at the given conditions actually. Okay, so at this given conditions, so fine, sorry didn't get you, मैं बहुत लेट हूँ, ठीक है, अब से फॉलो कीजिए, ठीक है, कोई दिक्कत नहीं सर, थोड़ा स्लो, हाँ ठीक है, नोट्स बनने के लिए कोई दिक्कत नहीं, ठीक है ना, क्योंकि ये पीडीएफ आपको ऐप में मिलेगा ना, ऐप में अपलोड करेंगे वो लोग बैकएंड टीम में, ठीक है. So now let's see what we are talking acoustic velocity. Yeah, see, I'll give you an example. I mean, we'll try to do some analysis. Let's say there is a duct like this. So there is a duct like this, fine. Now this is insulated duct. This duct is insulated. Okay, processing speed हमारी थोड़ी स्लो है, ठीक है. सर आपका टेलीग्राम ग्रुप, हाँ, आई हैव ऑलरेडी टोल्ड यू ना इन मेनी ऑफ माई क्लासेस, t.me/pw Vinay sir, this is my telegram group. Okay, no spaces in between, you can just type it. Okay, you'll find. So yeah, so let's see if there is a piston, for example, here, if there is a piston like this, if there is a piston like this which is initially in static condition, this piston is initially in static condition, this is static condition, initially it is in static condition, initially static initially, and let's say there is some fluid at this point, all over there is some fluid. Okay, so there is some fluid like this. You want to see all my lectures? Yeah, you can see in YouTube I have taken fluid mechanics, applied thermodynamics. Basic thermo is not on the on YouTube. Yeah, maths also not on YouTube, I guess. Fine, you can see definitely. Okay. So yes. Now let's see. Let's say, for example, this is air. This air is at some pressure P, density O, temperature T, and specific enthalpy H, for example. Okay. Now let's see. If I give a small jerk to this piston, let's say if I give some small jerk to this piston, immediately what happens? A wave, disturbance wave, a disturbance wave forms like this, and this disturbance wave travels at a velocity which is nothing but your acoustic velocity. Yes or no? Correct. So let's say if I just push this, then immediately at this point a disturbance wave gets generated, and this disturbance keeps propagating at a distance, at a velocity a in this medium. Okay. Now let's say definitely when this is moving like this, this part of the gas which is behind this wave front, so this is the wave front, disturbance wave front, disturbance wave front. Okay, so this is the disturbance wave front. So let's say all of a sudden it started to move this velocity dv. Okay, so let's say this piston all of a sudden it's initially a test, so all of a sudden it started moving at velocity dv. Then definitely by the time it just moves, this wave front gets generated, and this wave front travels at a velocity a. Okay, so behind this piston is moving at some small, let's say some elemental velocity, some small disturbance velocity which is dv. Okay. ओके, यू आर स्टडिंग सर, मैं लखनऊ रेलवे स्टेशन में आपका लेक्चर अटेंड नहीं कर पा रहा हूँ. ठीक है, कोई दिक्कत नहीं, यूट्यूब पे वो लेक्चर्स रहेंगे. सो डेफिनेटली व्हेनेवर यू फाइंड सम फ्री टाइम, यू प्लीज गो थ्रू दैट. ओके Ankit, yeah. So let's see if this is the case. This gas which is already here has already got some effect of this wave, but this gas which is here, they still don't know about this coming of the wave front. Yes or no? See, I'm repeating. Wherever this gas is there, or basically this part of the gas is already experiencing the effect of this wave front, so definitely some properties will get changed because it got certain jerk and they experienced. But this air which is here has not experienced yet the effect of this disturbance. Okay, means definitely here within this regime the properties might have changed to something like T plus dt, P plus dp, rho plus do, and H plus dH actually here, because this gas has already experienced the effect of this wave front. Okay, and this gas still it don't know about this shock. This gas still don't know about this piston movement and this wave front. This has this properties of P, rho, T, and H. Okay, now if you want to analyze what this wave front is doing, I want to take a small control volume around this wave front. Okay, I'm taking some small control volume about this wave front. Okay, so this is your control volume. Control volume. Now practically what's happening, look, if I take this control volume, understand carefully here, if I take this control volume, there's a wave front which is like this. This is the wave front, and this wave front is actually moving at a velocity a. This is what you know. But now this situation, if you write the equations with respect to this reference, you can say this as, practically what's happening, this gas is in static condition, this front is moving at a velocity a. Okay, you can also see this situation as, if you fix this control volume, means if you fix this wave front, let's say if you are sitting on this wave front, then it will observe like gas is coming into this control volume at a velocity a, and it is leaving at some velocity. Now try to understand. Frankly speaking, this gas which is coming at a should also leave at velocity a, but if this gas is moving at velocity a and this dv is actually pushing it forward, the relative velocity will be a minus dv. Yes or no? I'm repeating this point, see carefully. If you want to see the same situation by sitting on the top of control volume, like let's see if you are on the bus, okay, then you will feel this is stationary, then this guy is actually crossing at a velocity a, and behind the gas is leaving at a velocity a minus dv, because if the gas is trying to leave at velocity a, but this piston is pushing this gas again forward at this velocity dv, so this is a and this coming out is a minus dv. Is this clear to all of you? Is this velocity inlet and outlet to this control volume clear? Quick, come on guys, faster. Yes or no? Did you all understand that initially if this A is static and if this disturbance is moving at velocity A, now if you fix this disturbance at some particular location, you will feel this gas is coming at a velocity A inside and it's leaving at a velocity A minus dV outside, because this block is pushing this at a velocity dV actually. Okay, now clearly the properties are H, here it is H plus dH, it is T, this is T plus dt and all. Now let's see, if you apply mass balance to that control volume, mass balance gives you rho, let's say the area of cross section, of course it's same before and after because it's a uniform channel, so rho A into small is equal to, so this is the mass flow which is coming in, and practically this control volume is very small, it cannot hold any mass, so this is equal to rho plus dO, because the density in this part is rho plus dO actually, like I have told you here, it is rho plus dO times A into A minus dV is what you have. Yes? Yes or no? This is mass balance, simple mass balance in the control volume. Whatever mass is flowing into this control volume, same should leave. So definitely density times capital A into A is equal to rho plus dO into capital A into A minus dV is what I'm writing. Okay. Now if I simplify this, A and A gets cancelled. Rho A is equal to rho into A minus rho into dV plus A into dO minus dO into dV actually here. Okay. So this is what we get. Now let's see, if you cancel this OA and OA, and this is small variations because we are just taking it after the after this wave, disturbance wave. So this quantity is like higher order term, neglecting higher order term, because this density variation is like 10 power minus 4, then 10 power minus 4 into 10 power minus 4 of that order maybe. Okay, so neglecting higher order terms. So neglecting higher order term, because this is product of two differentials, which is small quantity into small quantity will be much small. That's it. Okay, so this gives you A times dO is equal to rho dV, which means your dV is equal to A times d rho by rho actually here. So this is one equation, means the velocity at which the piston moves dV will be A times dO by rho, and clearly if this dV is pushing it harder, see this guy do not move, this is static, and let's say if this is dV is very high, then definitely the density variation in this fluid will be large, correct? Yes or no? Correct? So please tell me, if this gas is in static condition and if this piston is moving fast, pushing it hard, then definitely this gas will be subjected to higher density variations. Yes or no? Means can I say in this channel, if dV is more, the density variations experienced by this fluid will also be more. Can I say this practically? Forget maths. Okay, so just see physics. If this piston is moving fast and this gas is not moving because this still didn't experience this wave, so definitely this gas which is in between the piston and the wave will experience high change in density. Yes, dV is proportional to dO. Okay, so change in the speed of the piston, or basically speed of the piston, is actually proportional to the density variations experienced by the fluid. Okay, this is proportional actually. Clear? Now if you do energy analysis, next energy balance. So if you do energy balance, okay, so if you do energy balance, let's see, at this inlet it has some velocity, A, and it has also some temperature T, because of which it has got some enthalpy. So H plus A square by 2 is equal to, similarly at this condition it has some enthalpy, H plus dH plus the kinetic energy at this point, A minus dV whole square by 2. See guys, because it is adiabatic, no heat interaction, no work interactions, no paddle wheel, nothing. Okay, no work interactions. Change in potential energy is neglected, so you have only kinetic and enthalpy. So change in kinetic energy plus enthalpy is equal to 0. So which means enthalpy plus kinetic energy specific at inlet should be equal to enthalpy plus kinetic energy at the outlet. That's it. Okay, so again if you simplify this equation, we have H plus A square by 2, H plus dH plus, if you simplify this, we have A square by 2 minus 2 times of A dV by 2 plus square by 2 is what we have. Okay, so this is the equation, simple math. If you substitute, 2 gets cancelled, this A square by 2, H goes down, 0 is equal to dH minus a dv, and you can neglect this because dv whole square. Okay, so dv whole square is dv into dv, so small velocity into small velocity, so definitely this can be neglected. So from this equation you can find out dh is equal to a dv, and everything is happening at isentropic case. Okay, reversible adiabatic case, so dv is equal to dh by a actually here. Okay, so dv is equal to dh by a, and if you look at your TDS equations, okay, so let's see TDS equations. TDS is equal to dh minus vdp actually, and this is 0 because we are doing isentropic reversible adiabatic flows. So your dh can be replaced with dp by rho actually. Okay, because dh is equal to vdp and v can be written as dp divided with density. Okay, now this tells you something, that your dv is equal to dh, which is dp by rho into this a, and this is under adiabatic conditions, s is equal to constant, otherwise this ds is not 0. Okay, so if this is not isentropic, you cannot put this ds is equal to 0, so this is isentropic, which means your dv can also be expressed in terms of pressure change at s is equal to constant actually. Okay, so this is one more equation. Now you can understand one thing, from mass balance you got dv is equal to some quantity which is 1, from energy balance you got dv is equal to some other quantity, but for consistency these two has to be same. Yes or no? Whether you calculate it from mass balance or energy balance doesn't matter, this dv has to be same in both the cases. Therefore from 1 and 2 this gives you here a times d rho by rho is equal to dp by rho times a at s is equal to constant, and this is also at s is equal to constant, because in this equation anyway, in this equation we haven't taken, but we practically know this is isentropic conditions. Okay, so let's see, this density and density gets cancelled, the denominator. You can understand, if this a is multiplied left hand side, this do is taken here at isentropic conditions. Yes, so a square is equal to dp by do at isentropic conditions. This is what you can see from mass balance and energy balance, simple mass balance and simple energy balance actually. You see, nothing big I'm doing, I'm just doing some equations. Okay, linear equation stuff. Okay, then you can see normally we have isentropic bulk modulus, because if this fluid is undergoing some compressibility effect, we can relate that to the isentropic bulk modulus. Isentropic bulk modulus, isentropic bulk modulus, you can see, if this is isentropic bulk modulus, es is equal to dp by do by rho at isentropic conditions. So this tells you es is equal to, this density can be brought top, rho into dp by do at isentropic conditions, and dp by do at isentropic conditions is equal to es divided by density. Okay, so es divided by rho actually here. Okay, so dp by do at isentropic conditions is adiabatic bulk modulus divided by density. So if I replace this with this quantity, you will understand, this implies your a square is equal to dp by do at isentropic conditions, which is also adiabatic bulk modulus divided by density of the fluid. Okay, that's why I was writing a is equal to square root of dp by do at isentropic conditions, and this is also equal to square root of adiabatic bulk modulus by density. This we have used actually in defining the first statement somewhere here. See here, when I'm talking about the things, you see we were replacing this quantity a is equal to root es by rho, that's the acoustic velocity, which is nothing but this is small a, which is disturbance of medium, disturbance of the velocity of the disturbance in the medium actually here. Did you get this? And this is valid, this expression. If you want to write this as one more thing, you can also write square root of 1 by rho into the inverse of bulk modulus is known as compressibility. Okay, so ks is adiabatic compressibility. We know in fluid mechanics we have studied compressibility. This is adiabatic compressibility. Okay, and ks is equal to 1 by es actually here. So if you write that, you can extend this equation, and this equation whatever I have written is valid for any fluid. So this is valid for calculation of acoustic velocity, because A is equal to A is the acoustic velocity, valid for calculation of acoustic velocity in any medium. Doesn't matter it's a gas, liquid, fluid, whatever, I mean gas or liquid, because I have never converted this dH in terms of Cp into temperature anywhere in this equation. Understood? Did I use, see, you can see the complete equation. I have never used this dH is equal to Cp into dt at any point in this equation. Okay, this is completely and purely based on enthalpies, and this is the expression that we have here. Clear? Last 5 minutes, I just want to show you one more thing, one last thing. Okay, so for ideal gas, definitely isentropic process, isentropic reversible adiabatic process. Let's write reversible adiabatic process. Reversible adiabatic process implies P rho power minus gamma is equal to constant. Correct? You know this. This is the isentropic process actually. If this is the isentropic process, if you differentiate this, let's see what we can do. First function into derivative of second function minus gamma into rho power minus gamma minus 1 times dO plus second function into derivative of first function is equal to 0. Derivative of constant is 0. Just differentiating the things. Okay. So if you differentiate this stuff, P power minus gamma into O power minus gamma minus 1 dO plus O power minus gamma into dP. Just differentiation. Okay. Now if you cancel this O power minus gamma, you will end up with the density because of this minus 1. Okay. So you can see minus gamma P by rho d rho plus dP is equal to 0. So this implies dP by dO in this case, where isentropic, because reversible adiabatic, this dP by dO is nothing but gamma P by rho actually. Okay, so that's how this definition is this quantity. So P dP by dO is equal to gamma P by rho by simple differentiation. Now if you use this in this equation, A is equal to square root of dP by d rho at isentropic conditions, and this guy is equal to square root of gamma P by rho, because at isentropic conditions dP by dO of an ideal gas is nothing but gamma P by rho. And if you know normally ideal gas equation, P, since P is equal to rho RT, because this is the ideal gas equation, P by rho is nothing but your RT. So this P by rho can be replaced with RT. That's it. Okay. So square root of gamma RT is nothing but your acoustic velocity only for ideal gas. You cannot use this for fluid, I mean liquids and all. Okay. So for liquids and all you can use this. Solids also you can use this. Normally, so let's say for example isentropic bulk modulus of steel is some value. You put the density of steel here, bulk modulus value here, then you will get, if you knock steel, at what speed the sound wave travels. Okay. Fine. Now are you all happy to see this? You see, nothing complicated I have done. It's bit of, you have to work out equations, but there's nothing complicated stuff in this. Okay, just energy balance and mass balance is what I have done for this control volume. Okay, clear to all? Yes. Yeah. This is square root of gamma RT. So this is how you can see basically in this equation. Now in tomorrow's class, because the time is actually short, I was not able to touch up this area velocity relations. So let's see, in tomorrow's class we will talk about in tomorrow's session we generally discuss about, tomorrow is the last class of course. Yeah. So in today's class we talked about psychometric process a bit. Process. Then we have seen some numericals. Then we started seeing compressible flows basics. Okay, compressible flows. So let's see in tomorrow's class. Tomorrow we will talk about area versus velocity relations. This is very interesting actually. Okay, so area versus velocity relations. Actually today what all I have done in this compressible flow is like a simple introduction to this. So this is very entertaining because you can see. So are we going to discuss about fan flow and Mach cone? Mach cone we'll discuss, but fan of flows is not in, I think we need not go up to a valley and fan of flows. Okay. If you want, I can discuss, but I think it's not needed for GATE. Because in the 3 years of syllabus, I mean, compressible flows was introduced in 2021. After that, there is one question on square root of gamma RT. One question is on some back pressure, which I'm going to deal in tomorrow in converging nozzles. And one question is again on this area versus velocity relations, which came in last year. Okay. So this we'll see. Then we'll see isentropic flows in nozzles. Isentropic flows in nozzles. We'll try to cover this converging and also converging diverging, CD, very important. Converging diverging nozzles, we'll try to see this stuff, okay, on this converging diverging nozzles. And third, we'll try to see shocks. Definitely I'll try to cover normal 100%. We'll see if time permits. We'll also, I think time won't permit by the time we come here. Fine, anyway, we'll see up to normal shocks. Okay, so normal shocks is what we will see. And if you need something beyond that, maybe I can take one extra class or something, but I think even till this point it's required. Okay, not beyond that anyway. Shocks also we are telling just as a safety point of view. Okay, because it's a relatively new topic, so that's why it's not introduced. But normally if you want, you can go into depths. Okay, fan of flows, valley flows, all these things, but I think it's not needed. Okay, unnecessarily why to engage the syllabus. Okay, fine, so that's it. Okay, I hope you all enjoyed this class to some extent at least. Okay, because compressible flows is like a very entertaining kind of thing. Please explain your group last question of steam function. Yes, the steam function question which we talked about. See, normally in potential flows, if you have seen that videos, psi1 is equal to x square plus y square, psi2 is equal to 2xy. Okay, if you combine these two flows, we can get the superposed steam function as psi1 plus psi2, which is x square plus 2xy plus y square actually. Okay, now this equation, if you take the conic section of equations, you might have seen for any conic section, normally if you take any cone and if you cut the cone with slant or straight, see for example, let's say if you have a cone, okay, if you have a cone like this, and if I take a plane exactly perpendicular to the axis of the cone, and if I make a cut, I'll see circle on the top, yes or no? Similarly, if I incline it and if I take a cut, I'll see parabolic, hyperbolic, different sections depending upon the way I cut my the way I orient my plane actually. Okay, now for any conic section, general equation is ax square plus 2hxy plus by square plus cx plus dy plus f is equal to some 0. So this is how we have the equation normally. Okay, now h square, depending, I'm not teaching complete math here, okay, because it's generally not required as of now. If you have this h square minus ab less than 0, this is the case of elliptic sections. Means for any elliptic sections that you cut, you'll see h square minus ab is actually less than 0. h square minus ab is equal to 0 is parabolic, and h square minus ab greater than 0 is hyperbolic. Okay, means for a section if you cut, if you put geometry, coordinate system, and if you try to analyze, if you set this HAB in this situations, one is elliptic, parabolic and hyperbolic. In this equation, if you compare this with this, you will see H is equal to 1, A is equal to 1, B is equal to 1 actually here. Okay, now x square, this is the function which is given, right? X square plus 2xy plus y square. Is this what you are getting? Yes or no? So please type in the chat box. H square plus guys, sorry, if this is 2h, then this is 4ab. Okay, so h square minus 4ab. A, just a minute guys. So this is, if this is h, then 2h whole square minus ab is what we have. So h square minus ab, correct. Okay, so this is h square minus ab. Yes, this is true. Now here if you see, h is equal to 1, a is equal to 1 and b is equal to 1. So if you calculate h square minus ab, then you can decide the nature depending on these conditions. Okay, that's how you have to solve. Clear? This is basically a bit of intro to conic sections, but anyway, that's not in syllabus. Even that question was in ESC, I think, very old question. 2003 before that. Okay, so basic knowledge of conic sections is required to solve that. Okay, so tomorrow is the last class. I wish you all will come back and we will wrap up compressible flows, and also if you have something to talk, you can talk, because I know tomorrow is the last class of this fast track also. Correct? Tomorrow with my class, I think fast track batch is going to end. Is it? Fine. Okay, so take care. We'll meet you again on 4th of tomorrow, 4 p.m. tomorrow, with continuation of this compressible flows. Hopefully I'll talk about this nozzles, isentropic flows in nozzles, which is again a very important and interesting thing, and we will talk about this shocks. Okay, normal shocks. Fine. And Mach cone as of your interest. PYQ says, so when will mathematics will start? Maths fast track has already started, I guess. No, not yet started. I think it is started now. No idea. Maths fast track is already started, right? If I think so. It has started. Fine. Ended. Good. Then syllabus is done. Okay. Fine. So we'll meet tomorrow at 4 p.m. Okay. So bye all of you. Take care. Bye bye.